All right, welcome. We'll be talking at the moment about message handling, how we handle different types of messages that exist. Message handling has always kind of somewhere entered in one of my talks, it seems, one way or another, and I've alluded to different ways, and talk about a particular way to do that now. So my name is Michael Caisse. I work at Intel in the chipsets Silicon Group. They take care of doing some embedded things, and it's what I've been terming lately deeply embedded. And so that's on the daily basis. We get to decide what ends up in hardware and what ends up in like silicon and what ends up in firmware, and making those trade-offs. I've gotten to do this a couple times in my career, and it's always a complete blast. All right. So messages are everywhere. You probably deal with messages somewhere. If you do some type of communication with networks, you're using messages. Those could be very low level, where you're dealing with bits and you're doing some binary type protocols, or maybe you're doing something with XML or JSON or whatnot. But we've got communication at a very high level, where we're just sending information around to different computers. If you're dealing with anything that has to do with vehicles, you've got communication all over the place, right? CAN is very popular, and so maybe a lot of the things you're communicating with are on a CAN bus, but you have all kinds of other sensors that maybe don't relate to that, or you've now interfaced. You have the CAN bus on one side, and now you have the sensors and the other bits and pieces on the other side that you need to now communicate with. Industrial systems, right? Whether it's robotics or just industrial systems, you're doing integration of a whole bunch of different bits and pieces inside of it. Again, you're communicating with messages to a lot of different types of devices. And they all have different protocols. They have different types of way to deal both with the hardware as well as the logical levels, what you do with the data when you get it, how do you verify whether it's correct or not. All of that type of stuff exists inside of industrial control. This is a shaper origin, even as you continue moving down. This is another project that I got to work on at some point. This is a really fancy router, is what this is. This is a router that has a motor that can move in X and Y and plunge up and down. You load into it the two-dimensional design that you want to actually cut. And it has cameras that can keep track of where you are based upon analyzing the grain of the board. And as you move around, it's constantly moving the bit to make sure that you stay within the realm of where you need to go. So you're basically the coarse movement, it's the fine movement, right? This thing's got tons of communication in it. Whether you're talking about the display or the buttons, or you're talking about actually the motor controllers themselves and how the higher level communication occurs, there's all kinds of different ways to communicate, data being passed back and forth, and we have to deal with those types of things in some manner. Well, it ends up that as you keep diving deeper and you get smaller and smaller, there are more messages. There are more ways to communicate. There are more ways to actually send data around, because there are lots of ways you could do this. You could have like data lines all over the place. Well, that wouldn't work real well, right? You're going to run out of room pretty quickly. And so you come up with protocols and ways to send messages. It ends up that the internet has this cool picture on it. So if you go to the internet, you can't get in trouble. So this is an Intel 12th generation. I work on this stuff at the bottom. And so at least this chipset, it describes, for this slide, that it's got a bunch of PCI. It has more USB than you would know what to do with. I have no idea what you would do with all these USB devices, but it has a bunch of USB devices. Thunderbolt, this PCI lanes, SATA. It's got down here at the bottom, you can even see we have eSPI and SPI, SMBus, all kinds of different audio capabilities. There's built-in Wi-Fi, there's built-in LAN. All of these things that you can see as a consumer on the outside somehow has IP components on the inside that have to take care of those. And something has to manage and communicate and control all of them. Make sure that they come up at the right time, they boot, they do the right thing with power, they stay maintained and do the right thing at all times. It's going to require a lot of communication again. In fact, I thought back in the day when I worked on industrial systems, like the systems that built these chips, I worked in in semiconductor manufacturing. I thought we had a lot of things that we had to talk to. But this works really well, not just for standards, but for protocols and messaging. It's like, oh yeah, well that protocol and message, let's just make another one because this one's dumb, right? And so they just keep propagating over and over and over and over again. And so what we would like to be able to do is to come up with ways to deal with messaging that makes our job easier. At least that's what I want to do. So the dying question, where do messages come from? Way back when we only had ones and zeros had not been discovered yet, we used cans and strings. But we've moved past that now. And so we do something else with messages. They come in through some type of hardware. The hardware converts signals of some sort. So whether it's current or voltage or some other type of thing that we're measuring differences of in order to determine what type of messages are coming, or excuse me, what type of data is coming in. This is usually a hardware driver of some sort. We're going to, in this talk, we're going to use two different terms. We're going to use a handler to deal with messages that are going up to our application, and we're going to deal with driver talking about things that are going back down to the hardware, okay? You may not like that terminology. That's fine. It's not your talk. It's my talk at the moment. And to be quite honest, Luke came up with the terminology. So if you don't like it, you can talk to Luke at the break, okay? Yeah, oh dear. What we would like to do is create abstractions. And in these abstractions, then we don't have to deal necessarily with the bits. So what do the bits look like? All right, so one general way to think about how messaging occurs is that there is some representation for our digital system, some representation that is in the physical world that is going to come in, and we're going to detect that, and we're going to detect it serially at the moment so that we detect one bit at a time. And as those bits come in, we're going to go ahead and shift them into the shift register down here. So we've got two of our bits in, and we'll just keep shifting those in until we get a full word. Once we have that full word, we'll go ahead and move that whole thing up into a FIFO. All right, so we'll just move that on up. And now we've got that word there, and then we begin shifting into the next set. We get the next set, and we keep doing this until we fill them all up, and then we turn on an interrupt. Now, we don't want to actually turn the interrupt on every time we get a bit in, because then we'd be very busy processing interrupt requests, right? We wouldn't be able to do a whole lot. And there's some balance between how much we want to get, how many bits before we get an interrupt to deal with it, and that granularity has to somehow be tuned at times. So once we get it, we can see our shift register at the bottom is empty. Now if we were to shift in a whole nother word, now we have a problem, right? Because maybe we didn't read out that FIFO, and so it's possible we have an overflow. There are all kinds of little bits and pieces that we have to deal with at the hardware level, but we don't want to deal with that all in our application code, right? So we want to be able to abstract that away. We want to, at the end of the day, take those bits and map meaning onto them, right? Semantic meaning. Otherwise, they're just a bunch of bits. So there's some meaning to these bits. We'd like to figure that out. So we have some goals with this message library. One is we would like to actually describe the physical bits. I guess we shouldn't use the word physical. The logical bits that have come in, those bits, we want to describe them and in the fields that they exist. So as we have this data coming in, we can think about certain bits have certain representations, and we want to provide that semantic meaning to them. We would like to be able to take those definitions and extend them. Say, like, here's the generic definition for this protocol, but here's a specific message, and be able to extend that a little bit further. We want to be able to perform data validation on the data that comes in. That's where you're going to end up with the most problems, right? Whether it's some user smashing your keyboard and causing you grief, or it's some malicious machine or not so malicious machine sending you data, you need to verify and validate that data. We'd like to be able to decouple our message producers and our consumers. They shouldn't know anything about each other. We would like to be able to set up our system in such a way that everything can be assembled so that they don't have to know about each other. We would like the system to provide easy debugging. So how many of you have ever done debugging with a protocol analyzer? Okay, so that's awesome, But then what happens when it gets inside of your software and it still doesn't work? Right? It looked really great on the wire coming across, and you used a protocol analyzer, and you're like, yeah, this is awesome. And then the software's like, I don't know, I didn't see a message, right? So it would be nice if there were some facilities to help us out with that. And we want to be able to have low resource usage. So at the end of the day, all this should be something a little bit easier. We're going to use CAN bus in our discussion here because my suspicion is a larger audience of people can think about CAN bus and relate to CAN bus in some way. So CAN bus comes across in the physical wire on this high and low signals, and you can see here then that the high and lows are actually doing the opposite of each other. And then based upon that, you'll end up here with the actual, what was the received signal. So it maps into that. The reason we do that is for noise immunity, so that if there's some noise spikes coming in, both the high and low, in theory, do the same thing. And so you're looking at the differential signals. You'll see some other interesting things about the CAN bus. So there's these things called stuff bits. So stuff bits occur because we have five repeating bits ahead of that. And so we have to stuff in a bit that is the opposite polarity in order to keep life nice. And so that's at a low-level driver level. Most CAN drivers actually just kind of pull that out for you. They stick it in and they remove it. So we don't usually see that in the data. You'll see it in the protocol analyzer instead, though. All right. And for an item, we're going to go ahead and use this GEMS RDM servo. It's just a servo. Like if you've seen those they look like playful dogs, robots that are about ready to take over your life. You've seen those, right? The ones that dance. A particular company makes them look really like harmless and cute. Anyhow, these are the types of things that are used inside their legs. And early last year, I was on a robotics project. We use these. They're very torquey. They're a lot of fun. So here is a sample response data that you might get from this servo. And you can see how it breaks this out. We have a command byte. Has then just this null. There's not going to be anything there. And in this particular response, we can see that each of the fields that follow, or each of the data bytes that follow, are a unique field having to do with PID constant values that are inside of the motor itself. And so we could query it, and we can get this information back. It'd be nice to be able to actually now deal with this data as it comes back, so that we're dealing with the actual field data. Here's another sample response. So this has a different command. This is the 9A command, and it has the motor temperature. We can find out a little bit of information about the motor temperature up here, right? Like what are the conversion units for this? It has in this null, and then 2 bytes are the voltage, null, and then the very last byte is this error state byte. And the error state byte is just 2 bits that represent error, and then everything else is invalid. So if they're set, life is bad, the motor has no idea what's going on. But the other 2 bits tell us about over temperature and voltage warnings. So this kind of lays out now the bits as they come in. Now let's figure out how we're going to map these. Right? There are lots of ways that we could approach this problem, right? Like, how would you want to approach it? I mean, this is the wrong crowd to ask.
40 people in the room, 60 different responses.
Yeah, maybe. I didn't ask that question. Okay, and the audience said, anyhow. So one way is like, if you've worked in any C code for very long, you'll find that features are kind of like, well, it starts off really clean. But then as features get added, it's like, well, I just need to write this out to the CAN bus, and I know where that memory address is, so I'm just going to write to the register. And pretty quickly, you have every feature either reading or writing to the low-level hardware. It doesn't start that way. It starts pretty innocent, right? People have good intentions. It's just that over time, it's hard to keep that abstraction. And I think this exists in a lot of code, not just C code, where the abstraction gets lost pretty quickly. We want to not do that. So you will have seen this slide in almost all of my talks recently because I am really a big advocate of this idea. And I'm a big advocate of this idea in a lot of ways. So how many of you think you get paid for twiddling bits in a computer? We'll talk later. You don't get paid to do that, right? Your company makes money because there's something that provides value. And that value that we provide generally isn't writing a state machine. Just use SML, all right? It isn't writing a bunch of different things that sometimes we get pretty excited about writing. That stuff is hardware specifics or other types of specifics. In this slide, it's called hardware specifics. The value that we provide as engineers, those are higher level things. And those generally, I would like to think about as the whats. The hows we get things done, the how bits, well, they're going to be like, yeah, I have to eventually twiddle a bit. I eventually have to understand that reading this register, when I read it, it's going to clear a bunch of stuff that's not going to be there anymore. Like there's like some mechanics that I have to get and understand. That's the how. So another angle of this slide is as we move up, we're talking about whats. We should be able to think about things declaratively. Because if we can think about things declaratively and we can write our code in a declarative manner, we're going to remove an entire classification of bugs. They just don't exist. They're not there. And it'll allow other people to look and be able to grok very quickly what in the world the thing's supposed to do, right? So we want to write our code in such a way that we're moving value up and we're pushing as far down as possible the hows. And as quickly as possible, we want to get back into this mode of operation in which we're talking about whats again, all right? So that's going to be another angle of the goal here. So let's just throw this up for a moment and see how we can work with this. At the bottom, we're going to have some hardware. This handler and driver are going to exist as concepts. We'll have a message abstraction of some sort. And our application is going to interact with the message abstraction. It'll have something called callbacks. So that it'll know when messages come in. And if it wants to go ahead and send something out, it'll somehow have to interact with the driver, but it needs to somehow do this in such a way that there's not coupling. All right? So let's solve this, the message abstraction first. So the message abstraction, when we think about a message, we're now thinking about a higher level concept. So we had these bits that came in, right? Maybe we had like 64 bits. And those 64 bits we can divide up into different fields, and those fields have meaning. And now we want to be able to map onto those fields that semantic meaning. We want to say, these bits have this particular representation. So one way of doing this, which I used to do a lot of, was like using boost fusion. For lack of a better word, we would do it differently these days, but it's the concept, right? And so how the technique works is you start off by just saying, the message is a struct. The struct represents my message. So I have a command and a motor temp and a voltage and an error state. And so I'm going to just now, from now on, I'm just going to deal with this struct. I'm going to adapt the struct. And all the adapting struct just means is that I'm going to run it through some preprocessor macro that's going to generate a bunch of template metaprogramming junk, so that I can go and look up information to let me convert structs into tuples with references. So we adapt it. We use the Fusion version. There are other versions out these days. From this, we now get something that is somewhat equivalent to this, where we can say, I want to say, as a sequence, something, and it returns a tie of then the elements that are inside. This is all generated through the metaprogramming thing. Like you could repeat fields, you can change fields around in the direction you want, things like that. So if you've ever done anything with Spirit or something like that, you've used this a lot, or a lot of Boost libraries use this. So this would be one way to go. And the advantage of this type of thing is we could just say, send our data, and it could take now that message that came in, and it's now able to understand the internal bits and pieces, and it's able to now do a send. And so the send looks like what? It looks basically like an apply where you take the type that came in, you take that value and you say as a sequence, and so now you have a tuple that maps to the values, or a tuple of references that map to the values that are inside of the struct. And you can call send_impl for each of those. Where the send_impl then is the different types that were aggregated together. So now we have like our uint8 or uint16. This is a very naive version. You add one level of abstraction on top of this again, and it checks to see if the thing is actually a sequence that it already has. Like, did it get out a sequence, and then it unwraps that. And so you can now create hierarchical data structures and only ever implement the leaves and do the fusion adapt. So it's really nice from an expansion, from a point of view of being able to write one set of things and be done with it. So it's declarative, it's non-intrusive, right? I didn't have to go and inherit from something to make a new type. It's easily extended, and we can either compose flat or hierarchical type things. So those are maybe the good sides of it. The bad side of it, though, is remember this silly thing? We had this error state. What was the error state? Well, the error state was like 2 bits. All right, so are we going to be able to take a reference or a pointer to a bit field? No, right, yeah. So this technique falls on its face right away just by using the adaption, because we can't actually get the bits that we want, right? We would have to add some additional capability to do that.
Still bit sets probably, can use vision handle bit sets.
In what? I'm sorry.
Bit sets.
Oh, bit set. No. Yeah, because you want to be able to treat these bits individually, and either you need to get you want to get a reference or a pointer or something to the data itself, and you can't with a bit field get a unique address, of course. So.
I believe you can get a bit field in C++20 though, right? You can designate bits for part of that uint8. I believe that is now possible.
All right.
But the reference part, yeah, I don't know. That you might not be able to do.
Jeff in library says that maybe this would work in C++20.
Somebody in this room knows. That knows more about the.
I don't know, but the person who knows is looking at it going, this is just a dumb idea, don't do this anymore. Right? Yeah, okay, great. Okay, so let's do something better then. So back to this again. We want to think more about our declarative things. We want to push up dealing with what's and the how's as far down as possible. So going back to our CAN bus servo, we've got this layout of our data, and we've got our bits inside of our status, and now we would like to somehow map those. So where are we going to go with this thing? So if we think about the bytes laid out, we've got something that's unique. That's the command identifier that came in, motor temperature, something that's going to be a padding. Voltage high and low, be nice if those were just voltage, right? Some more padding than our error states. Well, one way is we could just say that these map to fields, where the fields are the bit start and the bit end for each of the fields that have come into our message, to our data, and then a representation of how we want to view that data. So we're saying here that command consumes these bits, and I want to think about it as a uint8. And our voltage and status, our voltage status and our temperature status now, we're able to say that those represent single bits, and I want to represent those as bools when I deal with them. And so now we have this idea of fields. This is not written this way because we are in C++ 17 instead of 20, but we're going to pretend at the moment that we're using a 20 compiler and those look like strings, all right? Just because it makes the slide prettier. Ezra's shaking his head, it's okay. So I'm going with it now, all right? So we're just going to make it prettier. So now I think this allows us just to say fields, these are the fields I have, or in representation of what the fields are. And now I'd be able to say that I have a message that is made up of these particular fields. So I can see here that command, and it's not just any command, it's a command that's equal to some value. And I have a motor temp voltage, and then I've got my 2 status bits. How much memory I'd like to use under the hood for messages of these types. And then, again, another string, and we'll see that these strings come in handy a little bit later. All right, so now I have a type, that's the message type, that's composed of the different fields. So, I don't know, I think that's easier to read than what we had. Yes?
You could even use enums for command, voltage status, and temperature status.
You could even use enums for
For the command.
Oh, for the command.
And the voltage status and temperature status.
Yeah, these could also be enums. All right. Voltage, even though it came in as a 16-bit value, only 14 of the bits are actually valid, is what the spec said. So 2 of the bits didn't actually mean anything. And so in this case, I'm also just going to say that voltage is less than this value. If it's anything that's that value or more, it's actually, it's a validation error. What I got is not valid data. And so I might as well just build that in with my definition of what a valid message is. So this particular field is that. Now notice, one of the things that we did is we defined what the fields were, and now we're actually applying more constraints to the fields as we build up the message. So the fields are independent necessarily of building up the message. As I'm building the message up now, I'm applying more constraints.
So there were a bunch of bits in the message that were required to be 0 and aren't defined in any of your fields.
Yeah.
Is that the next slide?
No, I just ignored it.
Okay.
So
Just wondering, because it's like, you know, all those other status bits, you just say, yeah, if those aren't 0, we got an invalid message.
yeah, Marshall is bringing up the point that the other status bits that should have been 0, I'm not doing anything with. What I could have done is define the other status bits and then say that they actually have to be equal to 0 in the message. And so it become part of the validation of what this message means. Yeah, just didn't do it.
So it looks like the location in the stack of, let's say, voltage is defined in the type. But what do you do once you get to the situation where we have different messages where voltage is defined in different areas?
Oh, you would define a different message. So the question basically is like, yeah, voltage is defined in this particular location for this message. If we have a different message where voltage is elsewhere, we would define a different set of fields, and we would compose a different message type.
So you just enclose them in namespaces to avoid them collision?
Oh, would you give it a different name? Yeah, you could do that. Like if you didn't like, you could either put it inside of a namespace. Yeah, you could either put it inside of a namespace or whatever makes sense. Absolutely, yeah. Okay. Any other comments or fruit at this point? All right. So one of the things that we're able to do then with this is construct a message, giving it some data, and we can ask, is the message valid? We could also say, hey, get the under voltage status out of it. Get the temperature status out of it. So passing in field names themselves, we can then actually get out the values that we're interested in by the type that we've mapped to that value, to those bits in that field. On the other side, here we have now a message, and we're constructing it with field values. And we can ask, is it valid? Like, I've constructed one, but is it valid, the thing that I've constructed? Does it make sense? Or are some of these values actually not valid for this message type? And then I can actually set by field. So I can set a value inside of the message, passing it the field.
Does the constructor check that you listed all the elements, or what happens with the non-listed ones?
You can default elements. So fields, the question is does the constructor check whether you've listed all the elements? It does not. So you can list however many fields you'd like at that point. You can amend fields later. Fields have default values that can be provided when you define the message, you would define what the defaults are, or you can not define a default and you get value construction. Value construction. Okay. All right. So looking then at what a message data is. So message data contains data and the number of words that are currently being used. One of the things about messages as they come in and you have to deal with is the message has come in, the hardware memory is going to be used for something else. You need to do something with that message immediately, like copy it, or you need to be able to process it before it gets written over, right? And the easiest way to think about everything is just values. Unless it becomes a problem, don't do anything else, right? I don't know the number of code bases I've looked at where they're like, I don't want to be copying messages all over the place. Like, don't make that decision yet, because you're going to end up with all these other bugs because you didn't copy messages. Instead, just copy messages to start off with, and then see how bad it is. It probably isn't very bad in comparison to the other things that are bad. Okay, so we're just going to contain the information like that. Okay, so it seems like I tweet about this once a month, but for a different reason each month. So yeah, okay. So it's a non-solution. One of the things you would think, I have this message data. It would be really cool if I could just pass it an initializer list. That'd be great. And then I could construct the underlying bits with the data that came in, and it should just work great, right? And also, that part works great. And also, I want to be able to do this. I want to assert that the size is less than or equal to the size of the thing. I mean, everything that we do, if it compiles, it works. Daniel, right? If it compiles, it works. Like, we want correctness by construction. If I gave it something that was too large, I'd like it not to compile, right? Tell me about it. Well, it ends up like this fails, and the compiler says something very annoying to you, and it says, yeah, you can't do this because it's not an integral constant expression. I'm like, well, that sucks. Okay, so I'm pretty sure these were all constant things, so you go to CPP reference and you look, and sure enough, it's been const forever. So it's const, and it's been const expression since C++ 14. So it looks like we should be pretty good. And then you start thinking a little bit more, and you realize that's nice, except that this thing right here, source, yeah, source is our problem because source is not a const expr variable, and it can't be. And so Jeff heard me yesterday rant about this a little bit, but since I have more people who are on the standard committee just sitting here, I just want to take a moment. Please stop making hybrid types. If it's a type and it exists, like the initializer list, don't give me library access to access it and make it follow a bunch of rules that exist like that. Because of that, because this looks like any other type in the system, even though it's a core type and core knows that this is constant and it has a constant size and it cannot change, I can't get to it because of other rules, right? No, don't disagree with me. Gabber.
You can create an initializer list with the ternary operator based on runtime things, and boom, you don't have it in compile time anymore.
You always know the size.
But not at compile time.
You always know the size at compile time. You cannot create an initializer list without knowing the size.
You can, but you can choose between two of those at runtime.
You'll have to show me afterwards.
Okay, I can show you.
Yeah, if you break my theory, I'll apologize at Lightning Talks tonight. Okay, so this is like a non-starter, and so then what we do is we go, oh, yeah, Variadic templates solve everything in some strange way. And so now we use Variadic templates and we add some constraints so that things will work out. But what we get back is that we know that we haven't constructed a message that was too large. And that's fairly important to not overrun your buffer, right? Okay. And we could do this for standard array and other types and whatnot. And generally types, hopefully, that you already know what the size is as it's going in. All right, and then we've got all the other stuff that we're not going to talk about that's you either have or don't have. So let's talk about fields. What are fields? So the shape of a field, kind of what does a field look like? A field is primarily just a place to store a bunch of compile time information that we need to know about, right? But every once in a while, we needed to have a value in the field. So we'll go ahead and have the value in the field. So there's this name type up here, which will come in handy later. We've got where the MSB and LSB are. What is the type that we want to use for the representation? Do we want to provide a default value? And something that's called match requirements, which we'll see in a little bit. And then we can go ahead and have a value that's stored. Now here's the interesting thing, is if we use these in fields in such a way where we're never dealing with values, we're only dealing with the descriptions of the field, then the compiler is quite happy to optimize this, and we never end up with a value, right? And so while it appears that we have something there, it ends up that we end up with nothing there most of the time. It's only there when we need it. So, OK, fields. We can construct these, of course. That makes sense. And then we have two methods. One's called insert. And insert does exactly what you would expect it to do. Okay? It's going to do like compile time checks for bounds and bits. It's going to do all the bit shifting that's needed, and then apply all the masks that are required, and then just shove the data into the end result. So it's that's our insert. And it's throwing it into the data store, which is the data representation that it has, that underlying.
You didn't mean that to be const, right?
No.
Okay.
No, that one's not const. That's the unconst version.
Can you go back to your earlier point on the compiler optimizing? Go back one more slide, I think. So you're saying here that if you can construct a field with just the name, and then there's actually no T here? Is that what you're saying?
No,
Okay.
that would be wrong. We're not going to construct one most of the time.
You're just going to use the type.
We're only going to use the types. I'm sorry. Yes, we're going to use the type most of the time. We're not going to construct one most of the time.
Okay.
Thank you for correcting me.
No, I was just trying to get straight in my mind how that magic was going to work.
I should have gone with yes and let you, and then we would have had a new optimization.
Thank you.
Yeah. All right, so that's insert. And then the other side is extract, which then it does all the things you would expect, compile time checks, whatnot, extracts out of the data those bit fields, puts it inside of the data type that you want. So one nice thing about keeping this stuff under the hood, this is the how part, right? How many of you love default implicit integer conversions when you're doing bit operations?
My hand is in the floor.
Such a shock. Nobody raised their hand. Yeah, none of us like that, right? It's like such a disaster. And the reason for so many bugs is you do something that appears to be innocent, and the next thing you know, you have some integer sign type that you're playing with, and life is, not innocent anymore. So by keeping that code down below, and you're just dealing with the fields at natural types, then you eliminate a huge set of errors that are pretty common, at least in the bit twiddling type stuff. OK, so then we have field constraints. So we saw some of these earlier. This with required, so command has to have a value of 89 and less than a certain value. So how are the constraints going to work? So field, we're just going to create a little helper here called extend field. And that allows us then to pull out the things that we're interested in, namely the the name type, MSB, LSB, the type itself. And then there are going to be here some new defaults and possibly a new matcher. So with required is going to then extend the field and simply add this message equal to. And that's a matcher. So these are, it's added to it a new matcher type that will be there. And now we have a new type. And so how do the adding in, how does constraining fields work? Constraining fields works by actually creating a new type, right? And so you had the original type, you constrain the type by adding in more information to it. With less than, similar type thing, except for the matcher now is a less than matcher that's been added for the type. Okay. So then what's on the message side? The message side itself, we've got, again, a constructor of some sort. We want to go ahead and set all the fields that are associated with this to default constructed values, constructed values. So we're going to keep track of our fields. For set, when we set a field, we would like to make sure that the field is part of the message, right? This field belongs to the message type. And so we can assert whether or not this message actually has that field type. We can check field is contained within the field, meaning memory-wise, everything's nice. And then we can insert the data. So what does that look like? Has field is just checking to see if the types of fields that we have is of the list that we just now received, right? So is it the same? I like this because I like fold expressions a lot. So this used to be a disaster, right, to write this. What's that?
Well, it was my fault. It wasn't a fold expression before.
It's not a fault. It's a learning. Yeah, fold expressions are very nice. So we like them. They run, and they're const expert. So life is good. Okay. So we now have, we had this here where we're actually checking not the field, but the field ID. And the reason is because there are a variety of different things that we don't care about, right? The field ID, or how we want to think about the field, the important parts of the field, is the name, the unique thing, how we're representing this, the MSB, LSB, and the type representation. And those things are the uniqueness. The other constraints that we put on it aren't really part of the field, right? There are additional constraints that we put onto it. So we just need to check if we've got that. All right, so the other thing is then we could construct these, and we can pass it data, and we would like to now construct a message by giving that to the underlying message data type. And I forgot to mention that. So we're inheriting from the message data, and I'd love to talk to people about this later. This group in particular. Your feelings about this. I have mixed feelings. Moves back and forth. So we want to check to see if what we're constructing with are integral types, because then if they're integral types, then we have data that we're trying to construct, and we can go ahead and construct the underlying type. Otherwise, we have this other thing, like, is it a field type? If what we have are field types and we're trying to construct with fields, then we want to then iterate through those fields. First, we're going to set the defaults, and then we're going to set for the fields that we have. But there's this is field type. And so we have to somehow check if it's actually a field type. So what does this look like? Well, this is just using the detection idiom, because we're in C++ 17, to see whether or not the thing that we have is representation of a field type. And we have a couple different field types. We've talked about, in essence, the one in which things are contiguous. So the bits are all lined up right next to each other somehow. We also have disjointed field types in which, these 2 bits here and the 4 that are further down all combine together to make semantically a concept or a value that we need to deal with. All right. So setting a field type, we're just going to check if we have the field. If we have the field, we check to see if it's contained within, and then we can call this field insert, pass it the data. We already saw insert. The rest of it's an exercise for you guys later. So let's talk about decoupling. So that's the basic idea of that abstraction part. And the message abstraction is useful in itself, but if you just had that, you still have to figure out how am I going to attach everything together in such a way where I don't know about it, yet I'm using it. And there's this thing that we use called the constant build pattern. And Luke did a talk on this in IMBO this year, so about a month ago on this. Hopefully the video will be up soon. But the idea is that we have features and we have services. And features require services. Sometimes a feature might need facilities from another feature, but it never goes the other way around, right? We don't have services that point to features. Services generally are more stable, they provide something, and we would like these to get hooked up in such a way where they don't actually get hooked up in such a way where you're including all this information in the header files and they actually really know about each other, right? So that coupling would produce a problem. We have components. Components actually have services or features or multiple services or multiple features. Those components then are constructed together into a project, and the project represents this thing that you saw at the lightning talk when Luke mentioned the nexus. The nexus is basically constructing the project so that we can rapidly put together new things with new requirements at any particular time at compile time. So how does this work? There's, for example, you have your 3D printer. It works off a G-code, and you have a UART parser. The G-code thing is the service being provided. We've got a motor controller. In its initialization of the motor controller, it says that I'm interested in the move command. I'm also interested in the fast move command and the home command. Okay, those are the things that it would like to know about. Heaters, it wants to know about setting the temperature, and it wants to know about the heater off. And then fans, it would like to know about setting the fan speed and the fan off. So we have these different components now that have come together, and they've just said, these are the types of messages that I'm interested in receiving. And from that initialization now, the next part of the build time at compile time is the build. So we've initialized all the components. They've given their requirements of what they need, what they provide, and what they need. And now at the build phase, we're able to do some fancy whatevers, right? So for message handler, it's less fancy at the moment, but could be much fancier hopefully soon, where we now start constructing, because we have the graph at compile time, we start constructing the optimal way in order to provide the data that we need. And so this all occurs then at compile time. And when you watch the talk, you'll see like we have a whole bunch of different things where there are actions that have to occur in a certain order. There are dependencies on those. Each component doesn't actually understand the dependencies on the other one. We create the graph at compile time. We optimize the graph at compile time. We create the final solution at compile time. And we have a very optimized result at the end. So for like a single component, if you're just to do this as hooking things up, it might take you about 240 bytes of instruction and data to do like one of these little components. If you were slick and did it really well at runtime, in compile time, because all this happens at compile time, we end up with a final pointer at the end. The whole thing is like 16 bytes. So we see dramatic savings, as well as everything is completely optimized, ready to go. We're not doing function calls. Okay. So all of that to say, at some point, we register for callbacks. And so we're able then to say into these builders, these are commands that I'm interested in. And that's handled by the handler. You remember the thing that was pushing the data on up. So handlers are this abstraction then that's moving the data back on up to the application. So the registering part is within the builder, we add things that we want. And so we're adding here that we want callbacks. So remember our motor message. Let's go ahead and talk about it here a little bit more. Let's just say instead that we have a command field. We won't even add any additional information. We'll just say a motor message has a command. All right, so we're not going to constrain it. It's just generic motor message. The command always ends up there in those bits. So on the callback side, we can now go ahead and say, I want a callback, and I'm going to give it this cool name that I'm going to use in logging. And then I can give it additional constraints. Matchers have all kinds of different parameters and things that I can provide to matchers. So in this matcher, I'm saying match all, and all in this case, I want this field to be equal to a particular value. And then I can now have an overload set of the different functions that will go ahead and take care of that.
What's that SC UDL?
The SC, if you come to Luke's talk, you will learn all about, which I'll do another plug for in a moment. It's magic. I mean, it's not magic. It's a user-defined literal, but it's we do all of our string manipulations at compile time. It looks like format. It looks like FMT. And then what we do with them is we don't actually put them in the binary. They're not there, taking up room. We play some tricks at link time, pre-link time. And Luke will explain all the goodness there. It's very, very nice. Okay, so moving on here. We could then register now for here's our go callback, and maybe we had one for a stop callback. We could just keep adding our callbacks. We could also write this differently, and we could say, I have a motor message that represents, it's got a packet of 2 and some additional fields. So now I have my go, in which it is equal, command is equal to AA. My stop is equal to 77. And I'm just going to match always true and then let the types sort it out after that point. And so the way that you provide callbacks is pretty flexible in the system. These will then be determined as the message comes in, what matches the constraint the best. All right, the driver is very similar in which it just needs to ask for the thing that supplies the driver that's interested in, and it sends messages to it. So it doesn't know where it comes from. And it asks, again, with a compile time type. So all the compile, we just use tags, basically, right, to represent everything. OK, so one of the other things that is hard is when you've set up all of these callbacks in your system, but you're not getting them called. I don't know what's going on. Or the wrong one's getting called. I don't know why the wrong one's getting called. This is particularly a pain when it's in silicon, right? So just take whatever problems you have, unless you're in silicon, and they're worse. Because you suddenly are like, I don't know what's going on, but I have to debug this thing, and I have to understand what's happening. And so there are different ways, whether you're using like here's a piece of software that you could use for doing CAN bus. You could use protocol analyzers, right? There's a lot of ways to look. There's tons and tons of tools to be able to look at things on the wire. And sometimes we neglect, what do I do once it actually gets in to the system? And so here is an example of an unexpected message that we've received. So first we received a message, and then we get, the system tells us that none of the registered handlers claim this thing. So I have a message. It looks well-farmed as far as I can tell. But at the end of getting it, and I went to look to see who's going to handle it, Nobody claimed it. And then it gives you the list of all of the registered handlers and why or why not they might have claimed something. And so the technique is the F's and T's just represent trues and falses for the expression that follows. So here, my response handler, and it's looking at the source ID is AA and 77. So yeah, that's not a great match. Here, not a great match again. The opcode didn't match. And whatever this thing is over here, this looks like this matched. So we got a true here. And then this particular one, same type of thing. And it will continue on down the list showing us what is the reason, based upon all of the constraints that you've now provided to the message, based upon the fields, why those fields either matched or they didn't match, and therefore you didn't or you did get the callback. And so very useful technique inside the system. Now, how does this happen? It's really simple. Field just describe has a method called describe. And here's a little taste of what you'll see with Luke's talk. Looks a lot like the format library. So here we've got our curly braces. This is going to be substituted with name. Name is the thing that came into the field where we gave it a nice fancy name. So it's a compile time type. These are all known at compile time. It's being substituted at compile time to create a new string. This here is actually going to be a real value. So we're going to have to handle a real value at runtime in this spot. So the fields have this, messages have this, matchers have this. Everything in the system that can make a determination about and a decision about something has the ability to describe itself, its current state, and why or why not it's actually doing the thing that it wanted to do. Now the trick for this, as you can imagine in a small embedded system, is how to do it very, very, very fast and how to do it so it doesn't take up a whole lot of room. And I recommend that you go to Luke's talk. Okay. So I think like on the goal chart, we did okay. We were able to describe our packet layout and our bitwise structures. We are able to extend definitions, so we can define what a motor message looks like, and then we can actually go ahead and extend that to, or refine it so that it is refined further and further to make it a very specific message. We have data validation. It can tell us whether or not, in the logging, whether or not it matched and why it didn't match. That's really nice for debugging purposes. We can decouple using the CIB component. And the next steps. So that CIB component has been open sourced. It's available in GitHub. It is getting evolved constantly. As far as where it's at and what it does, a previous version of CIB exists in Silicon. So it's like, it's a thing. And so this is a thing that we use. You should go to Luke's talk on Thursday, find out more about the string bits. The message library, we're working on open sourcing that at the moment. So hopefully that will be done soon, and you'll be able to grab that and use it. You can use it with or without the CIB library. And I think we're doing actually some really cool things. Within the chipset silicon group, and specifically in the PMC team that we're in, we are kind of re-envisioning how embedded systems should be put together and built so that they are very, very reliable and that you have strong guarantees of what's going to happen at compile time. And so look forward, if you're interested in this type of thing, look forward to more talks about some of the work that we're doing, ranging from how we handle interrupts to all kinds of other fun things. And more libraries open source. Follow after Luke or myself on Twitter, and you'll get updates about those things. Any questions? Ezra.
You mentioned correctness by construction.
Yeah.
Are you concerned about being able to construct a message type, message object, and then have a period of time before you call .isValid? Being able to construct an invalid message. Is that a concern?
So the question is, am I concerned about being able to construct an invalid message and it be invalid for a period of time and something happened to it?
Forgetting to call is valid.
Yeah. I'm not, because the driver is going to make sure it's valid before it does something with it. So you can construct it in parts and pieces. You construct with what you may know at that particular time. You may not know all the information, and there are reasons sometimes you have to construct the message early. And then you will fill in the rest of the message as you're able to. But an invalid message can't be sent out because it'll be checked.
Yeah. To add another comment, for the most part, the requirements on messages is used for messages that are inbound to match the data to a specific message type. And then, like, when you create a message, like, you can't necessarily set the command if the command already has a required value for that message. It won't let you do that.
Do fields know how to deal with Indianness in any way?
Do fields, that's a really great question. Do fields know how to deal with Indianness in any way? No. Should they? Yes. I think that will be part of the process in which it becomes open source. These will be the types of things where we hope that other people will be involved and help out with that. So,
Is that just a little idea for you? You just use the correct Indianness.
you just use an Indianness.
So you, the messages that you demonstrated there were all very simple integer types. But of course, in general sensor systems and so forth, we have much more sophisticated things,
Yep.
like floating point types. Perhaps run through a function to come from an integer value and then be adapted into a floating point type. Another simple example, there's a time value, which of course is an offsets in some, time.
In some units.
In some units. And you'd like to be able to deal with those things, of course, in first class C++ types as well.
Yeah.
So I wasn't 100% clear how much your field abstraction could actually lift those kind of things and do sophisticated transformations. So
Yep.
could you speak to that?
Yep, I can. Yeah, that's a good question. So the question basically is, are field types flexible enough that they can understand things like time in weird clocks or some type of conversion where it's not just you've got some raw bits in, but the semantic meaning or the representation that you want to deal with is a representation that's more complicated? And the answer is no. And the reason it doesn't is because it's actually, this library is meant for getting the data as it comes in and how to map that into something meaningful. And the initial meaningfulness is an integer or a whatever, right? You're going to tell me about the handler.
I want to make one comment.
Yeah.
If it's convertible to and from an int, then you can use whatever type you want, right? So that's the way it is right now.
Yeah.
Not necessarily the best way, but that's how we can do it.
Yeah.
Well, I mean, the cases I'm talking about are things like, you got to take an integer, apply a polynomial function to it to make it into a floating point type, for example.
Yeah.
And, this is in the satellite telemetry domain is a continuous issue, right? Like, this is a thing we deal with.
Yeah.
All kinds of data points to do those sorts of things. Because in the hardware itself, yeah, it's actually just a number.
So what I would do, like if that was presented suddenly to me as like, this is an issue we have, I would say the first level of bringing something in is still, I've got bits. And I've got to, so that I have that first level of message, right? That handler then takes care of what is the conversion now into my next level of meaningful application data. And so it performs that transformation. That's now provided to the system. That's a service, right? And something can register for that as the service. So the conversion into your weird elliptical, whatever it happened to be, right, is a service that's being provided. And the data, whether it's coming from this point of data or maybe it's coming from something else, can be abstracted as now it's a data feed in your system.
So just one redux on bit field thing. If you go look at it, I think actually you can use bit fields to do what you want to do.
Okay, all right. Well, I mean, I don't want to do that.
Yeah. So yeah, with the caveat that the compiler may not path him the way you want it. So
Okay.
that could be a problem.
Yeah, that's a problem.
You show these matchers which have the range constraints, so values are in a certain range. And you mentioned that this is checked at compile time. Do you also have the situation where you check runtime values, or you get a sensor reading or whatever?
Yeah, great question. So as we're, the question basically is, some things can be checked at compile time. Some things also can be checked at runtime. The matchers need to be able to check at runtime. So if you put a constraint on a field, like the temperature values are always between these, anything out of that means that something's like totally whacked out about the hardware. As it comes in, it checks that it's a runtime value that's checking. So the matcher is making sure that that fits the constraint. Anything else? All right. Wow, it's totally lunchtime. What do you think? Lunchtime? All right. Thank you.